Okay, today's parametrics. I told the kids to get out their calculators, so they're doing that just because we're going to have to plot some points. We're not going to use parametric mode in the calculator yet, but when you do, you can get lots of cool patterns. Okay, some of you guys are talking when I'm talking, and that's not cool. Okay, thank you. So here we go. I'm fast forwarding through a bunch of stuff about the labs, and parametric equations have a different look to them than normal equations do, and it's because they have more information. Also because something that together combined doesn't pass the vertical line test like this, see, that wouldn't be a function, can be broken up into separate functions that are functions. So it's like you're doing more equations at once than just one, and yet you get one graph out of it. I think the best way to explain this is tying it to something you're used to. So everybody add a page and make yourself a little XY chart. This is X, this is Y, and we are back to plain old X and Y again. You know, you may recall that the last few units have been polar, which didn't have X's and Y's. It had what? R's and thetas. And then we did polar complex, which was in what form? Cis form, okay? And this is neither back. It's back to like plain old-fashioned kind. Now, let's say we had this equation. Y equals negative 4.9 x squared plus 7x plus 2. Who remembers the little pieces of these? There's one is this, and the other one's this, and the third part's that. You did this for like months back in quadratic algebra, and then again in higher algebra. Now you're in honors pre-calc. So what's the velocity? That's 4.9. That is the gravitational pull. That's kind of a velocity. That's gravity. Why is it negative? Because then your parabola goes like this. You know what I'm talking about? How high do I start my parabola? At 2, because this is the starting height. This coming back to you now? Okay, so now what's the velocity? 7. And this is important. People think of velocity as just like one thing. Okay, so if I threw this remote at somebody in the back row, do you get it would have more than one component? Oh, you had it, and then you lost it. So, does it have vertical component to it? It's okay. Tip's bent. It's okay. Toss it back. All right. That had vertical component and horizontal component, because from where he was, he had to throw it up to get to me. Do you get it had vertical component to it? And in fact, do you get he actually threw it a little higher and then it came back down to get to me? Okay, so it had vertical aspect to it. Did it also have a horizontal aspect to it? Would you say that in that 1 second it took from him to throw it to me, that traveled about, I don't know, 8 meters? So then he threw it about 8 meters per second. Okay, but that was horizontal distance. When you have this graph, you have x and y. And what is x? Time. What is y? Vertical height. Kind of redundant, but I'm trying to say vertical to make the point. What's missing? What don't we have in this equation? Nothing's horizontal. So, let me give you an extreme example. Little kid throwing a baseball. He's throwing his fastest fastball. Okay, but it's a little kid. We're talking like, let's say he's a 5-year-old. He's not going to get much speed on his fastball, right? The same exact equation could be a professional baseball player throwing a fastball. Why? Because on a fastball, is there a lot of vertical move? Vertical, up and down. Like, what's the highest a fastball ever goes? Maybe he releases it at 2.5 meters. Maybe it goes up a little bit, 3-4 meters maybe at the most. It does it go down the whole time? It might, but you get, at least if nothing else, there's not much vertical distance. Okay, So my point is, if this could be modeling a super strong guy throwing a fastball, or it could be modeling a 5-year-old throwing a fastball, do you get it's missing some info? It's not telling us the speed. It's not telling us the which direction, vertical or horizontal. Horizontal is missing. That's what parametrics can do, is they can add in that component. All right, so let me give you another equation for this instead that will give us that component. I'm going to change x to time. I mean, that's what it's always been anyway, so we're just going to call it t. That allows me to write a separate equation. I want you to think, what would that have to have in it, my second equation? Well, still need an x. So it's going to have x equals. And now x isn't going to be time anymore, though. Now x is going to be what? Horizontal distance. X is now the horizontal distance. Y is now the vertical distance. Now it's actually doing what I think some people thought it was doing in the first place. Do you get a lot of people think, here's you throwing the ball. Okay, you're standing here and you're releasing the ball from right here, and you're throwing it, and it's just how far away the ball was when it landed. That's not what it was. It was never that. What was this? This was time. That was not a distance away from you that the ball landed. That was time. So if this had been, let's say that this was at the point 8, 0, that means that it was in the air for 8 seconds and it hit the ground right there. It has time and it has the height of the ball. Notice no x distance. So this graph with this blue line, that could have been you throwing the ball straight up in the air and having no horizontal distance at all. And it would still look exactly like that. So it never had distance away from you. Now, on the graph we're about to do, it will have difference away from you. Distance away from you, I mean. All right, so let's see if we can plot a few points. Do you remember me saying the XY chart is your best friend in graphing? It still is, but it's not the XY graph anymore. What? It's got to have X, got to have Y. I mean, it's just still has X and Y, but it also has T. So it's the TXY chart. Everybody make one. This is going to be your best friend in graphing parametrics. When you get to graph them with a calculator, that's going to be mostly just fun. You'll just type them in and it'll be super easy. You just have to understand the window is the only thing that's complicated at all with parametrics graphing on the calculator. But doing them by hand, you need time and X and Y. Now this is really important. Time is not on the graph. Do you get if I only have an X and a Y axis, I can only have X and Y on the graph? So I can still tell where the ball is, like with the height that goes with a certain distance away from you, but I don't know at what time it is. I can have it on my chart, but I can't have it on the graph. So let's see how this would work. You know, in the old XY charts, wouldn't you always just pick a number and stick it in? Do the same thing, except you really don't want to pick an X or a Y. You want to pick a, what do you think, a time. And I'm going to, what's the easiest time of all to do? Time 0. Good. So let's put in time 0, and let's stick that into both of our equations. So wait a minute, we don't have an X equation yet. Let's say that our example just a second ago, kid throwing a marker, it went like, I'm going to call it 10 meters. It probably wasn't 30 feet. I'm going to call it 8 meters. Went about 8 meters in 1 second. Okay, so that's 8 meters per second. So would you agree that this, if I'm going to use seconds, was 8t? Does that make sense? In 1 second, it went 8 meters. So at time 0, I'm going to stick in a 0 here and here. And you'll have to use a calculator. Well, actually, you won't because zeros are so nice. What does y come out to be? 2. when I stick a 0 here, what does x come out to be? 0. 8 times 0 is 0. Now, does 0, 2 make sense? Why is x 0? It's not because time is 0. What distance? The distance horizontally is 0. It hasn't moved yet horizontally. Is it, why does it have a y distance? Because it's off the ground by 2 meters. That's why this has, because when you throw it from up here, it's a couple meters off the ground. Okay, good. So that's 1 point. And that's all you do is stick numbers in, plot them. It's pretty easy. There's more to understand about it, but that's really the basics mechanics. Is stick a number in, so stick in a 1. So now, go back in here, and this is where the calculator might be handy. If you could please put a 1 into that top equation. You do not need to graph it. You just need to type in 4.9 times 1 squared, which you probably can do in your head. And then plus 7 times 1 plus 2. And so y comes out to 4.1. Anybody verify 4.1? Okay, good. And then I bet we can do this one in our head. 8 times 1. 8 comma 4.1. All right, so now remember, this is not time. This is distance, 8 meters away. It's at 4.1 high. So let's say this is 5 meters. Let's say this is 10 meters away from us, 15 meters away from us. At 8, it was 4.1. Well, remember, this was at 2 meters starting height. That makes this about 1 meter. Makes this about 3 meters, 4 meters, 5 meters. Okay, so if I go with 8 comma 4.1, that's going to be about there for about 8, and 4.1 is like about there. Does it make sense that the ball would go up? Why? Because it's got, well, because it's got an equation that tells us how much it goes up. This is the equation that tells us how much it goes up. All right. And is this still the velocity? Which kind of velocity? Vertical velocity. Okay. All right. So now let's put in another point. Put in 2. At time 2, would you please figure out what the x and the y are? I know the x. It's going to be 8 times 2 is 16. You got the y? Negative 3.6. What the heck does that mean? It's gone through the ground. Yes. Imagine that this thing we threw was really heavy and it was landing in mud. It went below the surface. 3.6. All right. So then that's something that wouldn't have happened before. All right. So let's go with at time 2, we're at x is 16. That's just a little off my scale here, like right there, and it's negative 3.6. How could that happen? The cool thing is that we know where it is in space and time, and it's got to be negative. It's got to be below the surface of the ground. Maybe we were standing on a dock, and now it went below the dock. Do you get we could probably assume that the ball did not do that? So let's fill in some points in between. Like, what's something in between 0 and, this first reading we took, which was right here, and the second reading we took? So time is 0.5. Everybody put in 0.5 into the equations, and let's squeeze in a point here. 0.5 seconds. Where was the ball? X is what? Well, I can do that. Half of 8 is 4. And how about y? What? 4.27? That's all right. All right. So it's a little higher. It was a lot closer to us. So it was like here. Is that helping to fill in the curve? Okay. And somebody do 1.5 seconds. Just real quick, I can do the x part of it. X times 1.5 would be that'd be 12. And you suck in, what'd you get? 1.475. So then that's saying that when it's 12 feet away from me this way, that it's still up about 1 meter, so it's like about here. Does that make sense in the context of our curve thing? All right. So, moral of the story. Parametric equations is you have two equations that have three variables. Which one doesn't get graphed? T. And therefore, maybe you'll understand why we have to label it on our graph that was t equals 0. And that was t equals 0.5. This was t equals 1. This was t equals 1.5. And this one was t equals 2. Could I figure out at what time the ball hit the ground still? I could. What would you know? The t, the x, or the y? If the ball hit the ground. You'd know y, wouldn't you? What is y equal to? Y would be 0. The height of the ball is 0 if it just hit the ground. So if y is 0, oh, you'd get two solutions, okay? So then why is that? Because look at this. Wouldn't the line extend back this way too? And so you'd have two solutions, one over here and one over here. But we could solve for that, and that's getting kind of advanced, and I want to stop like going that way because we don't want to spend too much time on this. All right, so next thing is they'll always give you a time restriction. Would you agree that in the context of this problem, the problem stops making sense once the ball hits the ground? Okay, so we would say, would you agree that it's starting at 0, it's okay? And that's less than or equal to the time, which is less than or equal to, well, we know that 2 seconds it wasn't working anymore. 1.5 was still working. We'd have to solve it, but they would tell us that number, and they'd say like, it only works until 1.8. And they'll give you that restriction. Do you get that? That's called a domain. The domain for the time is between 0 and 1.8. All right. So I hope you've caught a few things. Number one, that the y equals x squared graphs that you were graphing before were only talking about the height. They were never talking about how far away it is. To get that, we need another equation. Parametric equations can do that. You'll have to always have two of them. And then there's two of them, but there are three variables, x and y and t. And then you'll always make an txy chart. And those are really as easy as you'd think. You just take 0, 1, and 2 for your times. Unless they give you times like, which they can, -1, 0, -1 to 3. Well, then you'd say, okay, I can make t -1 then. Sir? Yes, absolutely. So if we know y is 0, we could solve this equation for t. Yep. And then you could know the time when the height was 0. And yes, if you can factor it, you should. And if you can't factor, what? Quadratic formula. Okay. All right. So anyway, that's your intro to parametrics. They have more info, more equations, 3 variables instead of 2, and you can actually get like a vertical distance and a horizontal distance and a time all coordinated. All right, let's find the homework, and I'll do the first one with you. It's on page 26 if my memory is serving me. Looks like this, assignment day 1. We're actually kind of stretching this out because I got us going a little early on this. Technically, this assignment is happening tomorrow, but I'm doing it today. So I'm splitting it up so you don't have to know as much. Okay? So tonight's homework is just problems 1, 2, 3, and 4. And I'm going to do number 1 with you. Okay? So here we go. Convert to non-parametric form. What? I haven't showed you that yet, but it's going to be easy. What makes this parametric? The t. So basically, we got to get t out of here. So solve for t. Solve this one for t and tell me what you get. It's as simple as that. That's why it's one of the top 20s, is because sometimes these are complicated for kids, but solve for t. Did you get x plus 3 over 4? Cool. Then where do you put that so that we'll have an equation that won't have t's in it anymore? In for t. Yeah, t is x plus 3 over 4, so we put it right there. And this equation won't have t's in it anymore, because it'll now have x plus 3 over 4 in it. That is now an equation, y equals 6 times all that minus 2. And we do need to simplify that down. You can use a calculator if you want to, or you can just use your brain. Multiply it out and give me an equation with a slope and a y-intercept and all that stuff. So if you want to multiply this in, this would be 6x plus 18 all over 4, and then minus 2. And then this involves some factoring. Got to know how to factor in this class. Hopefully you can think this through and go, oh, well, I can get the 6 back out, which we already had, and then factor it into 2 times 3. All over 4, and this 4 can be 2 times 2. 2's cancel. Then it's going to be y equals 3x over 2 plus 3 times 3 is 9 over 2 plus 2. Y equals 3 over 2x, and 4.5 plus 2 makes, did I do something wrong? Oh, it's a minus 2. Thank you. Minus 2. 4.5 minus 2 then. 4.5 minus 2 makes 2.5. That's just algebra. And this is an exact example of why teachers often say, it's not the calculus that gets you, it's the algebra. Because this concept that I just showed you a second ago isn't that hard, but it's grinding out the math a lot of times gets people. Can you get it to there? I can tell you that is the right equation. Okay, now let me show you. That's the part called converting to non-parametric form. So why is this equation comfortable? Because it's got x and y in it, just like it always has. Why isn't it as good? What doesn't it have anymore? Time. So you don't know at what time things happened. You might end up getting a graph that looks kind of like this, but you don't know when this happened. You know where that is, but you don't know when it happened. And you might assume you can always just read them from left to right. You cannot. With parametrics, sometimes they go like this. You can have graphs like that now, where time is, maybe time starts here, and then time 1 is here, and time 2 it's there, and time 3 it's there. And so these get weird. Don't just act like they're the same as they always were. Okay, so how am I going to get my points? Well, if you just graph this one, it's going to be a line that goes forever in both directions. That is wrong. Why? Because time is only allowed between 0 and 1. So don't graph it based on just graphing this line. Besides, wouldn't that be a pain in the butt to try to find on this graph? But what we're about to do will show us the graph much easier than actually graphing it the old way. But I'm going to write this up at the top. Y equals 3 halves x plus 2.5. All that was you solving for t and plugging it in. That should be the easy part. Now, here's the new part. I don't think I want to call it hard part because it's not. TXY chart. Make yourself one. Have you already? If you haven't already, make this. And what's the first logical point to put in? Well, it says right here between 0 and 1, so let's use 0 for sure. And so if I put in time as 0, what will that point give me? Well, I stick a 0 in here, and I stick a 0 in here. And you can tell the x and the y really easy. What do they come out to be? X is -3, y is -2. So the point -3, -2 is on my graph. -3, -2 is right there. And I should label it with something else that's going to disappear. T equals 0. That's where it is at time equals 0. All right, now let's figure out where it'll be at time equals 1. Stick in a 1. 1 goes here, 1 goes here. 4 times 1 minus 3 is 3. No, it's 4 minus 3, which is 1 for the x. And the y, 6 times 1 is 6, minus 2 is 4. Do you agree that 1 comma 4 is my point there? Now, that's at time equals 1. Do you get that if I would have graphed this equation, it would have gone through those 2 points? Do you get that it will be a straight line? Why? Yes? It's not a quadratic, exactly. These equations here don't have squareds in them. Okay, so there we go. Why am I not going to draw an arrow through this thing and just keep going? It can't go that far. It stops at time 1. It's not going to go any further. Now, here's my last question. The time domain is between 0 and 1. Now that we've got this graphed, what's our x domain? -3 to +1. Remember, x domains go this way? And our range would be from -2, it's down 2 below here, right? -2 to +4. So there's all kinds of domains you can talk about. The furthest it ever goes up and down is from -2 to +4. The furthest it goes left is -3. That was over here. Furthest left it ever went was -3. The furthest right it ever went was +1. So that's the domain. So this graph has a domain and a range. And it's got a limit for the x's, and it's got a limit for the y's. It's got a domain of this one is, the x, I moved that by accident. That right there, the domain from left to right, that's the main domain that you'd be looking for. Because this one's already given. The time domain's there. It's just more like, what's the x domain then? The other one's called the range. I might have said this wrong before, but that's the range. Okay, good. So if I were you, here's a process I'd always use. I'd always make a TXY chart. And I'd always stick in my first 2 numbers that I would pick would be the whatever they tell you time can be at the beginning and the end, 0 and 1. And then you find the points that go with that and you graph them. And let's say it's here and here. Can you just always assume it's a straight line? Not always. But if there's no squareds, then you could. Last thing is, again, I'm just guessing. These points are not there. I'm just totally making stuff up. The last thing is you got to put it in non-parametric form, which just means you solve them. These are already solved for x and y. That doesn't help. You have to solve one of them for t and then stick it in the other one. And you'll have the old-fashioned equation. But that equation takes these 2 points that we're going to find from this chart, and it would just blow right through them and go forever in both directions. And that's not what these do. These have a limit on them. Very strict about the domain. Okay, that's parametrics, the beginning of parametrics. And that's all we have for the lesson for today.